All right, so after you have this, we can then use the cross method to figure out what the formula should be. So it looks like it's going to be Fe3. The 3 is coming from the nitrogen. So Fe3 and then N2. All right. So let's go ahead and work through a couple more. So I think in this next example here, let's go ahead and say copper 2. And we'll step it up a little bit. Copper 2 hydroxide. So once again here, the first thing you want to do is figure out what ions you have. So copper is a Cu. That's from the old name of cuprium. And we're being told it's a 2+. And you guys know what the hydroxide ion was? That was the OH negative. Yep. All right, so then when we bring the 2 down, that 2 goes to the entirety of the OH there. So you don't want to have it separate, meaning you don't want to have like an O2H2 there. We're going to have to use parentheses here. So we're going to have 1 on the copper, and then hydroxide in parentheses, and then 2. And let's see how much more you guys remember from 103. Should that compound be soluble or not in water? Should be insoluble. Hydroxides are typically insoluble, except for if you have like group 1 elements attached to it. All right, but we're getting ahead of ourselves. I just want to kind of get a gauge how much you guys remember from Chemistry 103. Because I really want to focus on the harder stuff in this class. All right, so let's switch back over to this. Desktop. All right. And alrighty, here we go. So formulas for ionic compounds, here's the general rules for it. We always put the metal first and its charge, and then you do the non-metal and its charge after. So basically when you write your formulas, it should kind of match the order on the periodic table. So the periodic table reads left to right. That's how you're going to write your formulas. So typically you're going to write cation first, anion next. And then you want to write the charge without the signs and add the appropriate subscripts. And you want to only use whole number ratios. And then you could check that the sum of the charges of the cations matches the total charge on the anions. That's where I was saying the total positive is equal to total negative. All right, so this example here, they did use the cross method here, but notice here we do not get the smallest whole number ratio with this particular example. So if you can reduce it further, go ahead and do so. So here we have a common multiple of 2 that reduces to 1-to-1. All right, this is similar to one of the examples that we did earlier. So we can use the cross method here to quickly get a formula. All right, so naming ions here. So a cation is named by simply stating the element it is. And if you're naming the ion, we just add the word ion after. But if you're naming it as part of a name, you just simply state the element that it is for the cation. The anion, the root of the name tells us which kind of anion it is. If we have an IDE ending, that is the case where it's monoatomic. It's just a chlorine. So no oxygen, nothing else is matched with it. It's just chlorine. As a little side note here, if you were to go to our chemical stockroom, and any chemical stockroom in general, if they're doing things right, they should be storing things by the anion, for example. So like if you go into our stockroom, we'll have a chloride shelf, a sulfide shelf, it's always by the anion because most of the reactivity actually comes from the anion. You do get reactivity from the cation as well, but most of it's from the anion. Okay, so common ion names. So if it's monoatomic, you just go ahead and name it, add its element. Here in the transition metals, we have the ones that have multiple charges there. I do want to point out that I am not making you guys remember the old-fashioned names. So we do have the old-fashioned names with the ick and the us on the names. So I'm looking at the bottom right corner here. The general way that it works, if you're curious, is us is the lower charge, ick is the higher charge. And they only use this naming on ions that have two different charges. So I would have this handy for the homework. I'm not going to put it on any quiz or exam, but you're going to need this for the homework. So, and I'm not a fan of memorizing the old way. Just go ahead and go with the new way. So, for example, cobalt 2 is this cobalt 2. Do not tell me cobaltus. It's cobalt 2. The only ones I've seen that are actually still commonly used are the ferric ferrous and cupric cupris. Those are still used, but all the other ones, not so much. Those are the old-fashioned names. And for the Game of Thrones fans out there, I want to point out that Tannis Stannis. So. All right, these ones you do need to know. And there is actually a systematic scheme for naming oxyanions. But first things first, I do want to point out the hydride ion is H-. That does exist. So if you see H as an anion, we're going to call it the hydride ion. And then we have some special cases here that you're going to want to add to your little note card for learning stuff here. So that's the cyanide ion. We did talk about the hydroxide ion earlier. And we have a new one this semester, the peroxide ion. That is the O2 2-. So if it's oxide, it is O2-, and then peroxide is O2 2-. Where have you guys heard that word before? Probably in your everyday language. The peroxide, you probably have that in your house. Hydrogen peroxide. That's actually H2O2, right? In general, if you see the per prefix in front of things, in chemistry that means extra oxygens. So peroxide is implying an oxide ion with an extra oxygen in it. And as a little aside here, if you have the concentrated hydrogen peroxide, say like 5% or greater, and you could throw in some raw meat into it and it'll cook it. It's kind of fun. It'll actually cause the foam to boil over, and after a few minutes, the meat in there will be cooked. And just warning, if you do that, it does not smell good. It does not smell good at all, but it will cook the meat. So quickly get through all the rules here. All right, so one of the big tricky parts here is remembering the oxyanions, if you recall. And I am referring to this portion here, the upper right. And I think I'm going to go ahead and switch back over to the document camera to explain it in a little bit more detail, because I want you guys to understand this. And I want you guys to remember them off the top of your head. But I want you to learn it rather than just, looking at a flashcard. I don't want you to learn it that way. I want you to just learn the rules. That way you can apply them as needed. All right, so .chem. Let's see if my software is still operational. It's still recording and it's still responsive. How awesome is that? All right. So I want to go ahead and use let's go ahead and use bromine for an example. So if we have just Br-, that is a monoatomic ion. So we give it the IDE ending. So this is bromide. Okay, and we then need, if we have oxygens on there, the oxyanion, that's when we start using the ate and ick and us endings on them. So if you recall, what I call the base version is the one with the ate on there. So that is the one with 3 oxygens. So this one has the ending of bromate, ATE. Once again, what that means is you have an oxyanion that has the base amount of oxygen atoms in there. IDE ending means that you have only that particular ion. There's no oxygen involved. All right, and if we take away an oxygen relative to the base amount, do you guys remember what the name changes to? Yeah, it becomes ITE. All right, and then what if we have only one of them? So we're going to keep the ITE ending, but we're going to go ahead and add something else to it to denote that we have one less. It's hypobromite. Yep, we add hypo in front. So hypo means less oxygen, and then you're saying the per means more oxygens. So we have extra oxygens. So this is hypobromite. And there's that joke that's on the internet, like saying, "Hey, do you have any sodium hypobromite?" Nah, bro. Because it's spelled out nah, bro. So, I know, very punny, I know. I like almost all chemistry jokes. All right, last one here is extra oxygen. So relative to this name, we have an extra oxygen, so we call it perbromate. And the per denotes extra oxygens. And 8 means it's from the base amount, which is 3. Okay, the tricky part with this is that some of them have a different amount for the base, for the ATE ending. And do you guys remember which ones they were? Like how to point them out on the periodic table? They actually make a 4 shape on the periodic table. So it's actually phosphorus, sulfur, arsenic, selenium. They make a 4 shape. So let me go ahead and bring it back to periodic table here. I know I got some. Where is it? Desktop, CSN. I know I had one somewhere. Let's just Google it. All right. Images. Hopefully you guys have your periodic table handy that I gave you guys, right? Oops, what am I doing here? I think I have one in my backpack, actually. Or you got the periodic table app, right? The one I showed you guys before, too. Let's just go ahead and bring this one up. I have it handy. Totally forgot about it. Anyway, the ones that have 4 oxygens in their base were phosphorus, sulfur, arsenic, selenium. So they actually make a 4 shape on the periodic table. So let me go ahead and grab some color here. So let's go ahead and use purple and highlight them. See if it shows up very well, but I recommend highlighting this on your table to remember that these ones have a different amount. They have 4 oxygens if they have an ATE ending. Thankfully, also, you're not going to see the whole variety of these. So, for example, you're going to have sulfate. Do you guys remember the formula for sulfate offhand? SO4, and then what was the charge? It's a 2 minus. So SO4 2 minus, that is your sulfate. The next one you're going to have to worry about is sulfite. And that has 1 less oxygen. So it's still following the same naming scheme. So I would argue that a common mistake with this here is a student seeing SO3, oh, it has 3 oxygens, that's sulfate. That's not the case. That's sulfite. So sulfate has 4, sulfite has 3. And just to reiterate here, the ones that do that are these ones that I marked here with the 4. And the other ones are actually just these guys. They're actually nitrogen over and then down. So I know it seems like I'm making you guys memorize a lot, but there's actually a systematic approach to it all, which is what I'm hoping you remember. All right, so with that out of the way, I do want to do a couple practice. So what if we had sodium sulfate? There's an easy one for you. So just like before, we go ahead and write out the ions here. And then doing the cross method here. You want to be careful. If you need more than one of these polyatomic ions, you have to use the parentheses. So this was Na2SO4, sodium sulfate. And this particular salt is commonly referred to as sea salt. So if you ever eat sea salt, compare it to like your standard sodium chloride, they have a little bit different of a flavor, and that's because of the sulfate ion. So you get most of the salty flavor from the sodium ion, but you're getting the slightly off flavor from sulfate versus having chloride. If you do like to have sea salt, I highly recommend that you get the iodized kind, because most people, I know I'm in this category. A lot of people do not eat seafood, and if you don't eat seafood, you need iodine somewhere in your diet, and that's how you get it. It's iodized salt. Then if you have high blood pressure issues, then you got to worry about other ways for getting salt. Then your iodine. All right, let's go ahead and do another one that involves these guys here. So what if we have So do you guys remember what ammonium was? NH4, and what's the charge? Plus, is it +1, +2, +1? This is one of the few polyatomic ions. It's the cation. Most of them are anions. So this is one of the exceptions. And perchlorate, so okay, chlorine is the base. And we have oxygens in there, and then from the prefix and suffix, I can figure out how many. How many is there? It's 4. All right, so after we have that, we then do the cross method to put everything together. And because we only need one of each, I don't need parentheses here. So NH4ClO4. Ammonium perchlorate. And if you remember right, the potassium perchlorate is rocket fuel. Yeah, we use perchlorates for fuel sources. And maybe I'll get Brian Leslie to do it for you guys, your lab instructor. If you take potassium perchlorate and actually heat it up till it melts, and then throw in a gummy bear, the whole thing will burst into flames. But you have to use a gummy bear. It's funner that way. You could use regular sugar, but it's funner with a gummy bear. All right. Let's go ahead and just do one more here just to make sure that you guys have good practice. So let's say we have magnesium. And let me think of a different one here we haven't done yet. Let's just go ahead and go with arsenate. All right, so do you guys remember the charge on a magnesium ion? 2+. We get that by looking at its position on the periodic table. And then arsenate is A. Yep. I also want to point out that I didn't mention here, but the ones that are in that 4 group, the one that have the different amount. So all these guys, their charges will match that of their monoatomic ion form. So sulfate being SO4 also has the 2- as sulfide does. And the same thing holds for arsenate as well. So it's normally arsenic has a 3-, and so does arsenate. All right, so when I do the cross method here, I notice I do need more than one of the arsenates. So I'm going to go ahead and make sure I use parentheses here. So we need 3 of the magnesiums, parentheses, ArO4, close parenthesis, 2. And as an aside here, how many oxygen atoms are in that compound? There are 8. Yeah, there are 8. Okay. All right.
Sorry.
Go ahead.
How do you determine what the parentheses as far as like?
Oh, if you need more than one of them in the formula. Yeah, it's when you need more than one of them. If you don't need more than one of them, you just go ahead and write it out. If you do need more than one, parentheses around the whole thing. All right. So let's switch over to desktop, back to the PowerPoint, and not making the best time, but it's okay. All right. So this particular sheet here does have the summary here. I'm hoping you guys remember this stuff. I'm not going to go over all the detail here, but I would definitely commit it to a note card and do practice. You want to be able to recall these off the top of your head. And if you can do them off the top of your head, the faster it's going to be, right? We're always going to put that emphasis on timing. One last thing here before we move on is I do want to mention here we have the ones that have a hydrogen in front. So for example here we have the carbonate ion, but it has an extra H in front. So we basically just add the word hydrogen in front of the naming of it. Also, you need to drop the charge by 1. So normally carbonate is a CO3 2-, by having the extra H in there, which basically is attached to an H+ ion, it drops the charge by 1. So we call it hydrogen carbonate instead. And what was the other name? Do you remember what else we call that? So we call hydrogen carbonate or bicarbonate. So you add the prefix bi on there in front. That's actually more commonly used than the hydrogen prefix. So I will tend to use the words bicarbonate, bisulfate, things like that, because that's actually what people use in the everyday lab talk, is the bi prefix instead. All right, so I think we have a couple new ones this semester that we did not cover last semester. I think it's like thiocyanate and the chromates as well. And the main one, new one here is the oxalate ion. I did not go over that one last semester. So make sure you memorize the new ones. Don't forget, you still have the old ones and the new ones now. All right, I think we did all this. So just summarizing up here, cation first, then by the anion. If the cation has a multiple charge, you need to make sure you include the charge. Yeah, these type 2 are basically the ones that use the Roman numerals. Those were the ones that were in the transition metals. Yep. All right. The last type here is where we don't have cations and anions. These are your molecular compounds. These are basically, or typically, all nonmetals. So everything is on the right side of the table. So carbons, nitrogens, oxygens, etc. They do not have a cation. So if you're being asked to show the cations and anions, you can't actually separate them because they're all nonmetals anyway, right? So you can't separate them. Because they do not have ions, we have to specify the amount of them you have. So we have to use the prefixes mono, di, tri, tetra, etc. for them. So you don't want to use these prefixes on the ionic compounds. Because for the ionic compounds, we can actually get their quantity by the name alone and then doing like the cross method to figure it out, right? These ones you have to be told. And that's because we have the issue of empirical versus molecular. So we need to make sure we say how many there are. Also, I do want to mention here that sometimes we will drop prefixes. And the main one is the mono prefix on the first element. That's typically dropped. You also have a little bit of weirdness with the vowels too. And I'll go ahead and do an example here for, yeah, let's go ahead and just do like a couple of these guys so we make sure that we're getting a little bit of practice of everything. So let's switch back to the dot cam before we do the acid stuff. All right. So let's start with a simple one. So when you're writing your formulas out, you want to be particular about how you write your symbols right. So for example here, if we write that, that's cobalt. And then if we write that, so initially you might think that it's monocarbon monoxide. We actually dropped the first mono. So it's carbon. And then on this one, monoxide. We don't say monoxide, we say monoxide. We kind of roll it all together. So carbon monoxide. All right, so let's go ahead and do a couple other ones. So by that extension, this one should be pretty easy. Carbon dioxide. Do you guys know which one is bad for humans versus which one is bad for the environment? Which one's bad for humans? Carbon monoxide. And the one bad for the environment is the carbon dioxide. You guys know why carbon monoxide is bad? Or those that had me last semester might remember. Kind of go off on that a little bit. Too many tangents, I know, right? Basically, it forms a covalent bond with hemoglobin in your blood. And your blood is no longer able to transport oxygen around anymore. And we'll actually revisit that point when we get to the Lewis structure stuff later this semester. Carbon dioxide is arguably bad for the environment because it is it's a naturally occurring greenhouse gas. And the reason why people keep tying carbon dioxide with climate change is because there is a notable growth in CO2 in our atmosphere, and people are correlating it with anthropogenic sources. So anthropogenic means human-caused. So there is a definite increase from the Industrial Revolution onward, where prior to that, it kind of went in a sine wave, where it's not holding perfectly constant. It's kind of staying steady, but over time, it's kind of having a general upwards trend. So we'll go over climate change more a little bit, but just you got to move on here. So what about N2O5? So this time we have more than one, so we have to include a prefix on here. So yep, di-nitrogen and is it pentaoxide or pentoxide? Yeah, so technically, if you write it out, you want to write out pentaoxide, but when people say it, people usually say pentoxide. They kind of roll it all together. But technically, it is pentaoxide. Don't quote me on this, but I'm pretty sure the online homework is set to accept either way on that. All right, so moving along here, let's go ahead and take a look at naming acids. So I really want to get to this before the end of class today. Oops. Did I switch this? Did not switch this. All right. All right, so naming the acid. So in order to name an acid, you must be able to identify whatever the anion is. Because recall that an acid is anything that delivers an H+ to solution. So the cation is always going to be H+. So we don't have to say that in the name. By saying the word acid in the name, you are implying that the cation is an acid. So once again here, the name of the acid is identified by the anion. If you have a binary acid, meaning that it's only H and whatever anion, meaning only two elements, we use the hydroic acid name. So for this one, we have H and Cl. We don't have anything else there. So it's chlorine, so hydrochloric acid. So what would be the name for HBr? Hydrobromic, right? You're only really going to see this stuff with the halogens. So hydrofluoric, hydrochloric, hydrobromic, hydroiodic. Those are the only ones you're going to see with these names. And a little funny aside note here. So we have the hydroxide ion. So chloride becomes hydrochloric acid. So if we had H and OH, that should become hydrohydroxic acid or water. Or the dihydrogen monoxide is another way to name water. So sometimes we have common names. All right, so if the anion contains oxygen, this is where we have the whole additional naming scheme. So if it has an ATE ending, it becomes ic acid. So basically, I want you guys to know the difference between having hydrochloric acid versus having chloric acid. Chloric acid would be HClO3. Hydrochloric would be HCl, and just HCl. So if the ion has an ATE ending, it becomes ic acid. If it has an ITE ending, it becomes us acid. So in short, ate becomes ic, ite becomes us. So here we have the sulfate ion would become sulfuric acid. And then you would just, if you're being asked to write the formula, you're just going to balance it out with the number of H's that you need. So what would the formula for sulfuric acid be? H2SO4. So H is an H plus 1. So we have to have 2 H's to balance this out. Since we're talking about climate change, one of the main causes of acid rain is actually sulfurous acid. So it turns out that in the atmosphere, if you burn fossil fuels, if they're not treated for sulfur removal, they will give off SO3, sulfur trioxide gas, which can readily react with water to make sulfurous acid, which then comes back to the ground. So that's mainly an issue in places that have fossil fuel burning and they're not treating their fossil fuels for sulfur removal. And if you actually go to the pumps, this is actually mainly an issue in diesel fuel. And I believe it's diesel fuel in the U.S. has to be less than 10 parts per billion. So that's meaning that when you're burning it, you're not putting a bunch of sulfur in the atmosphere making acid rain. And hopefully we keep these policies in place. Getting the whole political side again, but hopefully keeping these policies in place. All right, so once again here, you want to identify the anion, and then we use that to figure out the corresponding name. You're going to add the amount of H pluses needed to balance it out. So basically, it's going to match whatever your charge is, right? So if you have a charge of 2 minus, we need 2 hydrogens. You have a charge of 3 minus, we need 3 hydrogens, etc. Organic chemistry naming is completely different. So to give you an idea of how different organic chemistry is I'm actually going to be introducing this next week in organic chemistry in that lecture. And it's going to be the intro of it, and we're going to do a little piece of it for the rest of the year. So there's actually a huge naming scheme for organic chemistry, and we basically name things off of the number of carbons and how they are arranged. And you'll see in organic chemistry that things fit together a couple different ways. If you've taken any biology, you've probably heard about functional groups, things like that. That's actually part of the naming for organic compounds. It's what functional groups are, what functional groups are present, which carbon they're at, how many carbons you have, all that stuff comes into play. So we're not doing that in this class. So no organic compounds we're going to be naming, except for like methane. I think it's the simplest one that we name. All right, with 5 minutes left to spare. Actually, wait, let me see. 2 minutes left. We got it. So we are now officially done with Chapter 2. And I was planning on next week bringing in some practice problems to work on Monday. And then we were going to start into Chapter 3. I'm planning on slowing down a lot in Chapter 4. That's where all the new stuff is at. So I'm hoping you guys are okay with my speed. I know we're going kind of quick, but I'm hoping you remember Chem 103 stuff. And you're not actually learning all the stuff new. You're kind of picking up, okay, I don't remember that, I remember this. Focus on what you don't remember. But you got to do practice of everything, though, right? Just to make sure. All right, have a good weekend. Don't forget, I do have office hours throughout the week. It's all in the syllabus.